Welcome to Chapter 4, An Introduction to Probability. This is a fairly complex chapter. There's a lot going on, and there are going to be a lot of examples. So follow along here, pause the video if you need to work through an example. Make sure you take notes on the formulas. They're in your book, but you might want to take notes on them here too, and we will do examples in class. So some key phrases about probability are what is the chance that, or what is the likelihood that? So probability is about an event that's uncertain, and we're trying to figure out how likely it is that it's going to happen. There's a difference between is it possible, which means there's some non-zero probability, versus is it likely, which means the probability is higher than 50%, right? Is it more likely than not that it's going to happen? So those are our sort of natural notions about probability, and what we're going to do is try to put some numbers and have some rules for that. So probability is defined as the likelihood that an event will occur. And a sample space for an experiment is the set of all possible outcomes. So when we say an event will occur, it's one particular outcome out of the space of all possible outcomes. An experiment here doesn't just mean like a scientific experiment. An experiment could be you toss a coin, right? And if you toss a coin, hopefully only one of two things is going to happen. So the outcomes for tossing a coin are usually heads or tails. When you apply to college, there are a few possible outcomes. The first ones that come to mind are you're accepted or you're rejected, but there's also waitlisting, right? So maybe the outcomes are you're accepted to the college, you are waitlisted, or you're rejected. You ask someone out on a date, probably the outcomes are they say yes, they say no, maybe they say that's not a good time but some other time. So then maybe there are 2 or 3 outcomes there. If you roll a d6, which means a 6-sided die, and this is what you probably usually think of as dice, the little square ones, the outcome is going to be a number, and it's going to be 1, 2, 3, 4, 5, or 6. That's what you've got on the dice. If you have a horse race with 8 horses, one of the horses is going to win. Horse 1, horse 2, horse 3, horse 4, horse 5, horse 6, horse 7, horse 8, right? So one of those. Okay, so then an event is a subset. So the dice make good examples for these. One event could be what's the likelihood that you roll a 3, okay? And there are 6 possible outcomes. So we could even say the probability of a 3 is 1 in 6, which is about 16%. Yeah, about 16.7%. Okay. You could also say, well, I'm not interested in just one number, but I'm interested in the likelihood of rolling an even number. That would be an event. I roll an even number. And the even numbers on a d6 are 2, 4, and 6. So this is another way we could do this, is we could either say roll an even number, or we could list the outcomes that work for that. And those are 3 outcomes. So the probability of even is 3 possibilities out of 6, or 50%. Okay, so probability, if the probability of something is 0, then it's not going to happen. So, what's the probability that you toss a coin and you get a 6? That's 0. The probability, if it's 1, means that it's absolutely certain. So we could say if you toss a coin, what's the probability that you get a heads or a tails? Well, it's going to be one or the other. So that's 1. And in general, probability has to range between 0 and 1. So it's something. It's not negative, never negative. and it should not be bigger than 1, right? Because what would that mean? It's more than certain it's going to happen. Like, that doesn't make sense. Okay, so probability has to be somewhere between 0 and 1. If you calculate 1 and it comes out outside that range, then that's a good sign that something is wrong. Okay, so some other ideas are intersections, and intersections are things where you have two different things going on and you want to see if they have areas in common. So for our dice roll, let event A be the case where you roll less than a 4. Okay, so everything that's less than a 4 on the dice is a 1, 2, or 3. Okay, and then event B could be that you roll an odd number, and the odd numbers are 1, 3, and 5, right? And so what is the intersection of those two? Where do those two come together, right? And those two come together at 1. 1 is in both of those sets, and 3. 3 is in both of those sets. Okay, so the intersection of those would be 1 and 3. The complement of an event is anything that is not that. So if A is something, then not A is its complement. And so the wonderful thing is that the probabilities of the two of those have to add up to 1. Or if you know the probability of A, then the probability of its complement is 1 minus. So 1 minus the probability of the complement has got to be the thing. Okay, so they have to add up. And if you need to know the probability of the complement, you could take 1 minus the probability. 1 minus the probability of A, and that would give you the complement. So if, for example, A is I roll less than a 4, 1, 2, and 3, then the probability of A is 3 outcomes out of 6, or 0.5, and the probability of not A is 1 minus 0.5 equals 0.5. And another way to write that is A with a complement. So the probability of A plus the probability of A complement has to be equal to 1. And if you roll a d6, the probability of all of the potential outcomes added together has to be 1. Okay, so the total probability for anything in the universe has to be 1. So then we can sort of say, well, can we count the different outcomes we could get if we do different things? And here are a bunch of pictures of a whole bunch of things that you could count. So we could count like number of rings, for example, in that space compared to other things. And so counting asks how many possible outcomes are there, and n is a number of outcomes. And if all of those outcomes are equally likely, then the probability of any one of them is 1 over n. So with the coin, there are 2 outcomes, and the probability of an outcome of any particular one is 1 over 2, or 50%. Okay. For the d6, there are 6 outcomes, and so the probability of any one of them is 1/6, or 0.167. But honestly, we often just say 1 over 6 for that. So that's fine when you have a simple little experiment, but what if you have a multi-step experiment? So you, for example, toss 2 coins, right? And now you could get heads on both. You could get a head and then a tail. You could get a tail and then a head. And you could get 2 tails. Okay, so there are actually 4 separate sort of arrangements you could get, and you could say that the probability of heads is 1/4, heads tails is 1/4, tails heads is 1/4, and tails tails is 1/4, right? And we're going to sort of get back to that kind of an issue later, because that's an interesting case in itself. And that's not too bad. I can sort of figure out 4 different outcomes there. But what if I have 2 6-sided dice, right? Well, then I could get a 1 on the first one, and I could get a 1 on the second one, a 2 on the second one, a 3 on the second one, a 4 on the second one, a 5 on the second one, etc., etc. Right? I could get a bunch of different pairs. So how many pairs is that in all? Okay. Stop and think about it. I know I just showed you, but just stop and think about it for a second. So we have a formal way to figure this out, and this is how we do it. We say for k different steps. So this is step 1. This is step 2. Okay, etc. How many different outcomes are there? Okay, and what we do is we figure out the number of outcomes and then we multiply them. Okay, so for our 2 dice, there were 2 steps. This is die 1 and this is die 2. Okay, and each time it has 6 sides, so n1 is 6, n2 is 6, and so our space has 36 total outcomes. And the probability of, for example, 1, 1 as an outcome is 1 over 36. Okay? We can do another example of this. What if we do a d6, a coin, and a card? Okay. And so the d6 has 6 outcomes. The coin has 2 outcomes. And let's say that we're only interested in the suit of the card, right? And remember, those are like hearts, diamonds, spades, and clubs. Okay, so that has 4. Okay, and so now our space has 6 times 2 times 4 is 12 times 4 is 48 different outcomes. Okay, so that's still quite a lot of spaces there. Here are the 36 outcomes for the dice roll. Note that you can set this up in a fairly nice little table. And notice that there's only one way to get this. There are 2 ways to get 2, 1 or 1, 2. There are 2 ways to get 1, 3, 3, 1. Okay. There are 2 ways to get 2, 3, 3, 2. And 2 ways to get 4, 1, 1, 4. Okay. So there's definitely an interesting progression going on here as you move through this table. And just keep thinking about that. Okay, that's important for binomial probabilities. Okay, so we need a way to count, first of all of these different outcomes that we could have, and then say, all right, if we picked a subset, how many different combinations could we get in that subset? All right, so first we need to know that there are n factorial ways to assign n things to n slots. And n factorial is defined as n times n minus 1 times n minus 2, keep going until you get to 2 and then 1. Okay, so 5 factorial is 5 times 4 times 3 times 2 times 1 is 5, 20, 60, 120. Okay? And 3 factorial is 3 times 2 times 1 is 6. Alright? And you have probably, or you need, a factorial key on your calculator. It looks like that little exclamation point. Alright? That way you don't have to do it by hand. Okay, so then we can talk about combinations and permutations. And the difference between these is that combinations are a unique set, and permutations are taking that unique set and putting it in different orders. Okay, so if we go back and look at our dice that we just did, okay, 1, 1 is a combination. Let's call it combination 1. Combination 2 is 1, 2. Okay, how many permutations of this? There's only one, right? There's only one of those. But so there's basically 1, 1, because that doesn't sort of do anything different. But for this one, we have a 1, 2 or 2, 1, right? So if we start changing the order of things, we end up with more permutations than we may have combinations, right? Because 1, 2 and 2, 1, if you're trying to get a sum of 3, then either one of those is fine. Okay, it's the same sum, but the arrangement is different. And sometimes arrangement matters and sometimes it doesn't. So if we want to figure out how many combinations we can make, then the formula is for n items in x combinations. So how many combinations of n items arranged x ways? N factorial over x factorial times n minus x factorial. And these are crazy formulas, so just hang on, we're going to do an example in a minute. It's going to make it a whole lot better. Once we have a combination, a unique set of outcomes, then we can say, well, how many permutations could we have of the same size? Okay, and notice that we multiply by x factorial here, and that takes it out of the denominator. So now we just have n factorial over n minus x factorial. So this is a bigger number here, and so that means that c is going to be smaller, right? P, we're dividing by a smaller number down here, and so we're going to have more p than c. And so just like here, we had more permutations than combinations. Okay? And you can sort of think about, like, the more different items in the set, the worse that's going to be. So with combinations, the order of things does not matter. It's just a unique set. With permutations, order does matter. And so if you have a question where it asks you something in order, you're doing permutations, and it counts every possible order of the combination that you have. Okay? And these are the two formulas. So let's take an example with 5 jewels. Okay, so we have like a ruby, a sapphire, an emerald, a topaz, and a diamond. Okay? And we want to say how many different combinations of 3 jewels could we have, right? So we could have ruby, sapphire, and emerald. And that would be a combination. Okay, we could have diamond, sapphire, emerald. And that's a combination. Okay. Now, what if we had emerald, diamond, sapphire? Is that another combination? No, because it's the same as that, right? Just switching them around is a permutation, not a combination. So our question is, how many different combinations can we have of a sample of 3? Okay, and so if we have 5 items and we have 3 in the pick, then we're going to have 5 minus 3 on the bottom. Okay, and we're going to have, so we've got 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1, and that's going to be 2 times 1. Okay, now notice that we have 3 times 2 times 1 here and here, right? So since we have 3 factorial here, once we get to this, we can cross that out as well, because it's on the top and the bottom. Okay, and that leaves us with 5 times 4 over 2 times 1, which is 2. Okay, and that's 20 over 2 equals 10. So there are 10 different combinations that we can have out of these 5 joules. Now let's look at those. Here they are. Okay, so we have the red, the blue, and the green. The red, let's see, red, blue, green. Then let's do red, blue, yellow, right? Then red, blue, white. So we started with the red, blue, and then we added each of the 3 things. Then we're going to drop the blue out, and we've got red, green, and yellow. And then red, green, and white. Okay, we'll drop the green out, and we have red, yellow, and white. Okay, and that pretty much takes care of all we can do with red. Then we can go back to the blue and say, well, did we do blue, green, yellow? Nope, we didn't do that, right? Because everything else had red in it. So that's a good one. Blue, green, and then white, right? So that's good. And then drop the green out. Blue, yellow, and white. That's another unique one. Okay. And then we can drop the blue out because we've done everything we can do with blue. And then we just have the last 3, green, yellow, and white. We haven't done that combination. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? And the probability of red, green, yellow, red, green, yellow, red, green, yellow, right there. Okay. Is 1 out of these 10. Okay? So that's our combinations. Now, how many permutations could we make of ruby, emerald, and topaz? Right? Oops, that's not helpful. There we go. So, we have ruby, emerald, topaz. We could have ruby, emerald, topaz. Think of this like a birthstone ring for your mom, right? She has 3 kids and these are their birthstones. And if you put them in order, then maybe the ruby child is first. But it could be emerald, ruby, topaz. Could be ruby, topaz, emerald, etc. Right? So at some point we can figure out how many different permutations of these 3 we can have. Turns out it's going to be 6. Okay. So how do we figure out how many total permutations in all if we took any particular ordering of a combination of these 3 out of the 5 joules that we have? Alright, so now this is going to be n factorial, which is 5 factorial, divided by 5 minus 3 factorial, or 5 times 4 times 3 times 2 times 1 over 2 factorial. And that's the 2 factorial, right? So now we have 5 times 4 times 3, or 20 times 3, is 60, right? So we have 6 times as many permutations as we did combinations, because we had 10 of those. And that lets us know that each combination has 6 permutations. So how many permutations of ruby, emerald, and topaz? Well, we can have ruby last, right, and rearrange the green and yellow. We can have ruby first and rearrange the green and yellow. We can have ruby in the middle and rearrange the green and yellow. Okay, so 6 permutations of those. And if we wanted to get back to combinations, we would say we have 6 permutations of these 3 colors out of 60 total, or the probability of having these 3 colors in any permutation is 1 over 10, which is the probability of the combination. Okay, so once again, we can get from permutations to combinations. Either way we go, the probability of getting red, green, and yellow in some order is 1 in 10, or 10%. So there's very much a logical connection here. It's just whether you're talking about having it as just a unique set or whether you really are interested. Because what would be the probability of getting red first? So probability of red first with yellow and green, right? Well, that one is only 2 out of 60, right? It's that one right there and that one right there. Okay, and 2 out of 60 is a lot lower number, equals 0.033. Okay, and that's a lot lower than 1 over 10, or 10%. So it makes a difference if you're talking about things having to happen in a specific order. Okay? Alright, so some basic rules for probability. First of all, the probability has to be between 0 and 1. The sum of all probabilities for all outcomes must equal 1. And when outcomes are equally likely, probability is 1 over n. And we can use these basic rules along with our counting functions like combinations and permutations to figure out the likelihood of rather more complicated events. Now, you might be asking, well, what if the outcomes are not equally likely? Then what on earth are we going to do, right? And so it turns out that that relative frequency we were doing from our frequency tables in chapter 2 is super handy, because if the outcomes are not equally likely, then the probability is the relative frequency. Okay? They talk about this in your book in terms of a priori probabilities and observed probabilities and things like that. So take a look at that terminology and language. The idea here is that we have to have some kind of observed frequencies in order to be able to get the probabilities. So as long as we have those, we can use this. So here's an example. Don't know if you've ever seen these toothpaste packages before. But marketers will often do these. They'll come up with different packages and they will show them to potential consumers, and they'll say, which one of these do you prefer? So here's a study where we had 5 different packages, and we showed them to a bunch of different people. Let's see how many different people. 5, 20, 50, 90, 100. That makes it easy. Okay, so we showed them to 100 people, and we said, tell us which design you prefer. So 5 people preferred design 1. Okay, and the relative frequency is 5 over 100, or 0.05. So that's probability. This is 0.15, 0.30, 0.40, 1.10. And what do those have to add up to? 100, or 1.00, right, equals 100%, if we put it in percentages. Okay? So just like with probability, it has to add up to 1. So these are probabilities. The most likely package preference, or the one with the highest probability, is design 4 with a probability of 0.40, or 40%. Okay? And there you have it. So an event is sample points that meet some condition. So for example, you could say, what's the probability to win the lottery with the numbers 2, 11, 14, 34, 36. I just picked random numbers. So here we could say, what's the probability that you prefer, or that consumers are going to prefer either package design 1 or 2. Okay, so now we say, what is the probability of 1 or 2? And we have to add, so this is the probability of 1 is 0.05, plus the probability of 2 is 0.15, and so that is 0.20 is the probability that they prefer 1 or 2. Okay, what's the probability that they don't like 1 or 2? So if this is A, this is a complement, and that is 1 minus 20% equals 80%, right? Okay. Here's another one. How many family meals did you get together for per week with different relative frequencies? And then it asks you, what's the probability that the answer was 0? What's the probability that people got together for more than 4 meals a week? What's the probability that they got together for 2 or less? Okay, and so take a look at those, figure out the relative frequencies, and figure out what the probabilities for those are. Okay, I'm going to wait just a minute. You might want to pause the video here and write down these numbers in your notes. And then we're going to do these in class, I think. So I'm just going to be quiet for just a minute here. Okay, off we go. Into more complex and conditional probabilities. This is one of those Escher kinds of things, right, where if you look at this picture too much, your eyes are going to cross. It's kind of fun. So now we're going to talk about combinations of probability, and we need some way to translate between English language and symbols. So sometimes we're going to say and. What's the probability of A and B together? Okay, and that's an intersection, and that means if this pink circle is A and the blue circle is B, then we're talking about this purple in here. The intersection where they overlap, that's A and B. Okay. If we're talking about or, then we're talking about a union, because it could be either one or the other. In this case, A and B are independent, so there isn't any overlap, but there could be. And the symbol for that is like the regular U for union, and that means A or B. If you have trouble remembering which way the symbols go, sometimes I like to think A is for and if we put a little line across that, it looks like an A. And so the upside down U, when you make it look like an A, is the symbol for and. Okay? So try to get those two symbols into your head so that you recognize them. For and, you have to have both outcomes satisfied in order to say that it is in the set. If the two are mutually exclusive, which means there's no overlap, so like the picture down here on the right where they're not overlapping, they're mutually exclusive, and then the overlap is non-existent, and so the probability of that is 0. Okay. If they are independent and there's not overlap, then or if one does not depend on the other, so that knowing about one doesn't change the probability of the other, and we'll get to that in a minute, then we say the probability of A and B is the probability of A multiplied by the probability of B. Okay? If either outcome will satisfy the condition, then it's a union, and the formula for the probability of the union is probability of A plus the probability of B minus the probability of A and B. And why do we subtract that? Well, we subtract that because if you look at this one on the left, right, the probability of A is this whole thing, and it includes this. The probability of B, let's see if I can get this to change colors. Okay, the probability of B is this whole thing, and it also includes this, right? So if we just take the probability of A and the probability of B and add them, we're double counting this thing in the middle. And double counting will overstate the probability. So what we do is we subtract it, but we subtract it once because we don't want to also just completely throw it away, right? It's in both of them. We want to count it once, but not twice. So we subtract it once. In this case, right here, there's no overlap, right? And so here, probability of A and B is 0. So it's 0. And if it's 0, then it doesn't matter. We can just add A and B. Okay, so when they're mutually exclusive, then this worry over here goes away. Let's do an example, because that often helps. So we have basketball championships, and we have the Atlantic Coast Conference and the Southeastern Conference. And they both do pretty well. So ACC has had a team in the championship 10 times out of 20 years. Okay. SEC has had a team in the championship 8 times out of 20 years. And 1 year, they were both there. Okay. So that's like saying, here's ACC. Here's ACC. And here's SEC. Okay. And 1 year, they both had a team in. SEC has 8 in all, so it had 7 unique ones. And ACC has 10 in all, so it has 9 unique ones, right? So 9 plus 1 is 10, 7 plus 1 is 8. The probability of ACC is 10 over 20 is 0.5. The probability of SEC is 8 over 20 equals 0.4. And the probability of both ACC and SEC is 1 over 20, or 0.05. Okay, so what's the probability that at least one of them will be in the championships? If we do this with the formula, then we have to take the probability of A, let's see, probability ACC plus probability SEC, and then we have to subtract probability of ACC and SEC. That is a mess. Okay, so we have 0.5 plus 0.4 minus 0.05 equals 59.85. Okay, and the probability that neither of them, so probability of not ACC or SEC is 1 minus 0.85 equals 0.15, right? The other way we could figure this, if we can do the Venn diagram, which is hard to do sometimes, but in this case it's not too bad. would be to say, all right, the probability of one or the other is equal to 9 plus 1 plus 7. So that's 17 over 20. Get out the handy calculator here. 17 over 20 is 0.85. Okay, 0.85 is what we found down there. So, learn to do it with the formula, but if you find the Venn diagram helpful, then you can also try to think about what the Venn diagram looks like. Remember, it's easier to start by putting the overlapping one in the middle and then subtracting that off from the totals of both as you get the parts of them that are distinct and unique. Okay? Alright. So that's sort of joint probability, which is things happening together. Conditional probability is about things happening kind of in sequence. So what if we know some information? We write this with a line going up and down. That's not a divide, it's an up and down line, although sometimes it looks like a divide because it's hard to get your keyboard to do a nice job with this sometimes. So the probability of A given B means that we already know B. Okay, B has already happened, or it's prior information. And knowing that may change our assessment of the probability of A, right? So now we know some information, and that may make us think differently about A. And so one of the basic formulas for that is the probability of A given B is the probability of A and B jointly divided by the probability of B. This is the base probability of B. Okay? So that's a basic formula that we can use. So let's go back to our Minnesota Vikings and Packers and our Coke and Pepsi. All right. So here, and let's sort of take this PA given B is PA and B over PB, right? So PA given B is probability of A and B over B, because we might want that. All right, so let's just start with what's the probability that somebody likes Coke? Okay, so we have 8 people total for Coke, divided by 20 is 0.40. And what's the probability that someone here is a Vikings fan? Okay, so we have 10. So that's 10 out of 20 is 0.50. And notice that these are based on relative frequencies, right? This is there's not necessarily an equal likelihood that you're going to like Coke and Pepsi. There is an equal likelihood of liking Packers or Vikings here, but there doesn't necessarily have to be. So we're doing this on the basis of the frequencies. Okay, what is the probability that they like Coke and Vikings? All right, well that's the 6 here divided by 20 equals 0.30. And what's the probability that they like Coke or the Vikings? Well, remember we learned that that's the probability of Coke plus the probability of Vikings minus the probability of Coke and Vikings. And we just figured those out, so that's 0.4 for Coke plus 0.5 for Vikings minus 0.3 for both, and that's 0.6. So Coke or Vikings is 0.6. Okay? Now, what we're going to think about in a minute is what if we ask the probability of liking Coke given that you like the Vikings. Okay, so let's sort of look at that for a minute in the table. Probability that you're a Coke person given that you're a Vikings person. So there are 10 Vikings people, right? And out of those, there are 6 Coke drinkers. So we could say the probability of Coke given to Vikings is 6 out of 10 is 0.6. All right, and we're gonna look at that in more detail in a minute. One of the things that we can do to help us with that is to convert this table from frequencies to joint probabilities. Okay, and so the joint probabilities are looking at inside the cells, what's the number there compared to the total. So if we go back, our Coke Packers cell is 2 out of 20. Okay, so 2 out of 20 here gives us 0.1, which we put here. Okay, our Packers Pepsi is 8 out of 20, so that gives us 0.4. Vikings was 6 out of 20, that gives us 0.3, and then 4 out of 20 gives us 0.2. Okay. Notice that these the sum is 1, right? So those joint probabilities have to add to 1. Now, we also can notice that this is 0.1 plus 0.3, and 6.6 is 0.4 plus 0.2, right? So if we add the rows, or if we add the columns, then we're going to get the total, row total and column total probabilities, and those are unconditional probabilities. So that just means that we don't know any prior information. We just say, what's the probability, for example, that you're a Green Bay fan, and that there were 10 of those out of 20, and that's 0.5, and that's what we get if we add those joint probabilities in that row. Okay, then 0.4 plus 0.6 adds to 1, or 0.5 plus 0.5. So when we add the row totals or add the column totals, we should also get to 1. Okay, so that's a handy little thing, because then if we think back to this formula, we have those pieces now, right? We have A and B, that's the joint probability inside the table, and we have the B, that's going to be a row or a column total. Okay, so now let's go back to this question of the probability of liking Coke given that you're a Green Bay fan. And we did it first by looking at this table here. And we said the Coke Green Bay, once we know that we're given that it's Green Bay, we're in this row, right? Given Green Bay means we're in that row. Okay, and in that row there are 10 total. The Coke drinkers in that row are right here, so there are 2, and that equals 0.2. Okay, notice that that is not the same as that number, right? Because this number is 0.2 divided, sorry, not 0.2, is 2 divided by 20, not 2 divided by 10. Okay, so that's the idea of a conditional. Given that we know we're in the Packers row, okay, that changes our assessment of the probability. Now we can also do it using this formula here. Okay, so same thing. Probability of Coke given that you're Green Bay is the probability of Coke and Green Bay, right? So that's there. That's 0.1 divided by the probability of Green Bay. All right. Well, here's the probability of Green Bay. That's 0.5. Okay, and 0.1 divided by 0.5 is 0.2. which is what we got that way. All right? Why all the gyrations? Well, because information can be given to you. Information can be given to you in very different ways. It can be given to you in raw numbers. This is a frequency table. It could be given to you that way. It could be given to you as probabilities this way, or it could be given to you maybe just as the joint probabilities inside, and then you have to figure out what the total probabilities are on the edges. Now, once we have this idea of conditional probability, we can use that to judge whether events are independent or not. And this is a definition. Events are independent if, and only if, the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B. Now, what does this mean? This means that if this is the same as this, that the probability of A given B doesn't matter if you know B, because it's the same as the probability of A. Okay? Knowing B gives you no information at all, because it doesn't change your assessment of the probability of A. Okay? Now, we could ask this about our team COLA problem, right? The definition would be that they are independent if the probability of C given GB is equal to the probability. Now look at how this goes, right? It's the first one, so it would be equal to the probability of C. And that means that if knowing that we're looking at the Green Bay line doesn't make any difference, then the probability of C is going to be the same either way. Now we calculated the probability of Coke given Green Bay, and that was 0.2. The probability of Coke by itself, if we look back up at our table, okay, here's our Coke people here. The probability of Coke by itself is 0.4. All right, so 0.2 is not equal to 0.4, and these variables are not independent. Okay, so your preference does seem to depend on which team you like. In this case, if you're a Packers fan, you're much more likely to like Pepsi, and if you're a Vikings fan, you're a little bit more likely to like Coke. Okay? All right. The other thing to work on is sort of making this a little bit more complicated to allow you to sort of track back to initial causes using a probability revision model called Bayes' theorem. Okay, and it looks really ugly when you first look at it, but it really isn't too bad at all if you start sort of parceling it out. And so you start with this notion of the probability of something given something else. Okay, and we're going to call that first something A1. And A1 has a complement, sort of A1 complement, and we're going to call that A2. Okay, so A1 and A2 are complements, and between them they are the universe. It's either A1 or it's A2. Okay, so the probability of A1 given B is the probability of A1 times the probability of B given A1. So you see, you take this and you flip it, and you go from A1 over given B to B given A1. And then the cool thing is that this top part is exactly the same as this bottom part. All right, so if you can get the top part straightened out, then you just use that again in the bottom part. Then the rest of the bottom part is the same as the first part, except instead of A1, you're going to use A2. Okay, I'm going to put A2 in there. So it's not too bad. So if we know someone likes Coke how likely is it they are a Vikings fan? So that's saying, what's the probability that they are Vikings given that we know they like Coke, right? What's the probability that they're a Packers, which I think we're calling Green Bay, given that they like Coke? All right, that's what that is asking. So let's do this. So the probability that they are Green Bay, given that they like Coke, so this is A1 and this is B, okay, is the probability of A1 times the probability of B given A1, and then this has to be exactly the same. Okay, and then we're just going to switch to A2, and so if you're not Green Bay, you're Vikings, so that's A2. All right, and now we could actually do this. Okay, so the probability that you're Green Bay is 10 out of 20 times the probability that you're Coke, given that you're Green Bay, is 2 out of 10. Okay, and so we're going to have 10 over 20 times 2 over 10. And then the probability that you're Vikings is also 10 over 20. And the probability that you're Coke, given Vikings, is 6 out of 10. So you've got 0.5 times 0.2 over 0.5 times 0.2 plus 0.5 times 0.6 equals 0.1 over 0.1 plus 0.3 equals 0.1 over 0.4 equals 0.25. Okay? And you can go ahead and do the one for the Vikings given Coke. So Green Bay given Coke, we just figured that out, is 0.25. Remember we figured out Coke given Green Bay is 0.2. We figured out Coke is 0.4. And from this comparison we figured out they're not independent. And we can also go back and forth between Green Bay given Coke and Coke given Green Bay using our different formulas if we want to. Now, the thing about Bayes or any of these is it is a lot easier if you can just look at the table, because somehow that just really makes a lot of sense to us, right? Once we get used to reading the tables, we sort of look at the number and we divide it by the right number and it's fine. But sometimes you don't have the table. Sometimes you have information from a previous study, or you only have part of the information, and so you really need to be able to use Bayes. The thing about Bayes is to work from the word problem you're given and set it up so that you know what the beginning part is, so that you know what this A1 given B is. Okay, so you want to get P of A1 given B straightened out, and then you know what A1 is. You know that A2 is the complement of A1, so whatever is not A1 is A2, and you know what B is. Okay? Bayes' theorem is used for factoring new information into your assessment of probabilities, and that's discussed in your text, and that's a super useful idea for all kinds of things. You're going to see that later in your careers and later in your courses. So Bayes' theory idea is a really, really useful one for a lot of things. One more thing that people often like to do with probability is to do a probability tree. And these are also useful for when you do decision trees in other courses and later. So let's see what this looks like, and this is going to help us when we think about binomial probability distributions too. So what if you toss 3 coins? Okay, and we know that on any given toss you get 50% chance of heads, 50% chance of tails, right? So coin 1. We're going to toss it, and we're going to get either heads or tails. Okay? Let's say we get heads. Then we toss coin 2. Okay? 50% shot we're going to get heads, 50% we're going to get tails. Let's say we get heads. Then we're going to toss coin 3, and 50% chance of heads, 50% chance of tails. Let's say we get heads. Okay? So now we've got heads, heads, heads. That's the only place we're going to get heads, heads, heads. And the probability is 0.5 times 0.5 times 0.5 equals 0.5 times 0.5 times 0.125. Okay. The next one, we're going to have heads, heads, tails. And the probability of that is 0.5 times 0.5 times 0.5 equals 0.125, right? But are there other ways that we could get 2 heads and a tail? There are actually, right? We could get heads, tails, heads. Okay. Or we could get tails, heads, heads. Okay. So those are permutations of the combination 2 heads and a tails. Okay. And so the let's put it over here. The probability of 2 heads, 1 tail is 3 times 0.125 equals 0.375. Right? Let's switch colors again here. Okay, and let's look at the next option. So maybe we go heads, tails, tails, and the probability of that is 0.125. But there's 2 more ways we could get 2 tails and a head, right? We can go tails, heads, tails. Or we could go tails, tails, heads. So there are 3 permutations of that combination, and so the probability of 2 tails, 1 heads is 3 times 0.125 equals 0.375, right? And then the last combination is tails, tails, tails. There's only one way to get that. Okay, and so now we've got our total probability for 4 combinations of 0.125 for the heads, 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 plus 0.375 for the heads, heads, tails in any order, plus 0.375 for the tails, tails, heads in any order, plus 0.125 for the tails, tails, tails equals, wow, 1.00 total probability equals 1.00. I have to write that out in the margin and have it show up. All right. So when you do a probability tree, you can look at these combinations and permutations, and you can also figure out what everything should add up to, because it should all come out to 1. And here's the summary of the different outcomes. Notice we can deal with this as an outcome frequency table with a probability. This is a relative probability of each individual outcome times its frequency to give us the total probability of that combination. And that is probably enough to start with. And now you need to get some practice, because there is a whole lot of shoving of numbers going on around here. Good luck.